All right. So so the recording is started. So we can begin the lecture this week, and we'll basically continue on from lecture 4, where we talk about branch prediction, right? So today we'll expand a little bit more from the really basic branch prediction to something that looks a little bit more of the CPUs of the like 2000. It's not a CPU nowadays, but still, right? Some more advanced topic in branch prediction and how it involves the way it record the history of your if else and for loop. And then we'll move on to the next big concepts about this will be like a preliminary to the concept called out of order processing. But we'll then talk about how to squeeze out the performance of the CPU even further, right? But then you also still need to preserve the sequential semantic. So we'll talk about what are those. So before we begin, let's review the lecture 4. Lecture 4, we talk about control dependence, which is something as simple as an if else in your code or for loop, right? So these things, the reason why we call this control flow is because they actually control the flow of your execution, how your program run, right? If some condition happen, you go into the if. If another different condition happen, it goes into the else part of your program, right? And the same thing goes for the for loop, right? Where if certain condition happen, you loop around. If certain condition doesn't happen, and you exit the loop. The thing is, when you think about the pipeline, right, you need to figure out like how do we actually handle the branches, right? Because one of the most basic thing we can do is to stall the pipeline, right? But the problem with stalling the pipeline that we learned from the last lecture was that you don't really know an instruction that is a branch until decode, right? Which means that if you want to start the pipeline, you insert the bubble one every other cycle, which is a really inefficient thing, right? And architecture is about efficiency, how to squeeze out everything as you can from the hardware as possible so that you can accelerate and make the program faster, right? So stalling the pipeline is an easy solution, but it's not efficient. So we'll now talk about other better solution, right? So last week we kind of talked about, okay, if you want to do a better guessing, if you want to guess the outcome of your branch, like whether it's going to the if or whether it's going to the else part of your branch, what are the information that we really need? First of all, right? Every single instruction, it can be a branch instruction, or it doesn't have to be a branch instruction. It can be just an add or multiply, right? So the first thing we have to figure out is that a branch? Is the instruction that the program counter is pointing at the moment, is that a branch instruction? The next thing is, let's say it's a branch instruction, right? Is that taken or not taken? Then we need to figure out the target, right? The target of the address. So basically, if you want to break this down to a flow chart where you have instruction coming in, is this a branch, right? Is that a branch? Yes, it's a branch. Or no, it's not a branch. If it's not a branch, you do PC plus 4. You fetch the next instruction. If it is a branch, you have two choices, right? Are you taking the branch or are you not taking the branch? Then if you're not taking the branch, means that you go to the next line of your assembly. You basically do PC plus 4 as well. But if you run into the if else and you take the branch, if you take the branch, it means that you jump somewhere, right? Then if it's at this step, you need to fetch next PC, right? As some address that you're jumping to. So you need to figure out where is your target that you jump to. And we established last week that we can use the structure called the branch target buffer for that, because the program counter has the perfect information. When you compile your program, right, if you have a branch like a jump in assembly, or a branch in assembly, like branch if it's not equal, for example, right? Then the program counter that points to that branch instruction stays the same. So you can use the program counter as an index into both the branch target buffer and the direction predictor. So the branch target buffer will first figure out, is it a branch? If it's a branch instruction, then it would check, right? It would check, should I take the branch on top, right? Or should I not take the branch? Which is, you just basically do PC plus 4. If you're taking the branch, right, next PC would be your target that comes from here. If you're not taking the branch, next PC is PC plus 4. Right, so this is not taken, and this is taken. And that's all, right? So with this structure called the branch target buffer, we established that we can use it to find whether it is the branch or not. By looking at that table, if the table has something there, it means that PC is a branch. Then whatever's in there is the target, so you know the branch target as well. The rest of the question is, hey, do we take the branch or not, right? So we talked about last week, we talked about this last time predictor. And as the name suggests, it's as simple as what we did last time, we'll predict the same thing. If I go into the if, the last time I see this if else, I'm going to predict, I will predict that I'm going to the if else. If I'm not going to the if I'm going basically going to the else part of your code, the next time I see the same code again, I'm going to jump to the else part, right? So that's the last time predictor. And you can basically build a state machine by basically label the left node predict taken. Basically, if you are here in this node, you are going to predict you take the branch. In reality, if you predict that you're taking the branch, but in reality, you're not taking it. So you jump to the next state, which is predict not taken. And the same thing go to the other state. If you're not taken, but in reality, you take the branch, you jump to the predict taken state. Otherwise, you stay in the same state, right? And you can implement the last time predictor in the BTB, right? As simple as something as this structure I'm showing you, right? You have the program counter coming in. The program counter uses the part of the address as an index into this big table. The index basically tells what row am I looking at. Then you use the tag to figure out, is that my PC? This allows you to search the table faster. You don't have to search every single row. The index allows you to search just that one row, and then you compare the tag. The tag table in the branch target buffer store some part of your program counter. And if the tag match, it means that I have a PC that's supposed to branch. Then you check whether I should take the branch or not. That's the second step, right? So again, the first step is to check the tag, right? This is the first step. The second step is figure out, do I do PC plus 4 or do I do the target? If I do the target, the third step is to get the target from here, right? And go there, right? Sorry about that squiggly line. Not supposed to do that. But basically that's it, right? You try to figure out where do I jump to. This way you can always guess, right? And if you guess correctly, you don't have to stall. If you guess incorrectly, you stall a few cycles because you have to wait until execute to figure out what the outcome of your branch. Then you have to flush. Flush means whatever I fetch, I throw it away. Because I haven't reached right back, I can throw my instruction away and refetch the correct instruction, right? So this also means that my worst case scenario, I have to wait until execute, which is not really ideal, right? So we want to make sure our prediction is better. So we kind of end the lecture with the two-state predictor using the saturating counter. Basically, you have 2 bits for your state. You can be strongly taken or strongly weakly taken. If you're in a strongly taken, you're going to predict taken. And if you actually not taking the branch, so if you're taking the branch and you're in a predict strongly taken, right? This one strongly highlight, not highlight. And if you're in a strongly taken state, you stay there. If in reality you don't take the branch and you move to the weakly taken, right? And then if you're in a weakly taken state and you actually take a branch, you go back to the strongly taken, and you don't take the branch, then you go to the weakly not taken. And the same thing goes for the predict not taken, the weakly not taken, and strongly not taken, right? The same logic applies. Any arrow with the red arrow is not taking the branch in reality. The blue arrow means that I'm taking the branch in reality when I run the code. So is this good enough, right? So can we kind of wrap this up with, so control flow is more frequent in your code as you think, actually. It can actually appear in like maybe about 10%, actually, around 10% of your code. So your fetch address is not going to be determined by after end cycle. I need to figure out whether I take the branch or not. And if we fetch m instruction per cycle, because today we'll learn how to fetch more than one instruction per cycle, you're wasting a lot of instruction that you have to throw away and flush them away, right? So it's a really, really good idea to make sure you can do a more complex branch prediction that can reach 97 to 98%, right? So now let's go with the more advanced topic, right? So now we are moving to the actual new material of the lecture, not the one from last week. And we'll talk about the two-level prediction, the global view, the one that takes into the global view, and the other one that takes into the local view of your code, right? So the question is, how do we improve the branch performance? And similar way to like most research and how it's done, we do research by observing, right? We have to be observant when you want to be a good scientist. So we can observe the first thing, that the branch outcome is correlated with other branches outcome. If I do something earlier, it gives me some hints into what's my likelihood of my choice I have to take right now. So that's called the so basically, if I have an if else in your code, and inside that, there's another if else, right? Those two branches, those two if else have correlation, and this is called global branch correlation. And the similar thing happened when you look at the same if else, but the next time you run into the same line, of course, that line that have if else, that's called local branch correlation, right? The past outcome of the same branch also have the effect into the outcome of the current branch. We'll look into the design for each one of these observations by first begin with the observation 1, right? If I have a branch that looks something like this, right? If condition 1 happen, A equals 10. If A equals 0, it should be double equal. If A equals 0, do something. This is branch 1. And this is branch 2. If I go into branch 1, do I ever go into branch number 2? If I take the first branch and set A to be 10, do I ever go into branch number 2? No, right? If I set A to be 10, I never have to go to the if part, right? So if the first branch is taken, so if you take that branch, the second branch you don't take the branch because you don't go into if else, right? The question here is then, how do I detect this, right? Because we just established through our observation that can be correlation in your branch, right? That can be correlation in your branch. So the idea is, well, on top of tracking, right? Given one individual outcome from the 2-bit, right? 2-bit saturating counter, you just look at the 2 previous if else. It can be anywhere in your program. Now, instead of doing that, we then track the outcome of each individual branches, and we detect this global decision on what happened. This global decision, we call them a global history register. And we'll go through examples to kind of explain how this works. All right, so bear with me with the definition for now. We will try to use this global history register to detect on a global level what's my branch outcome pattern. Then you look into each pattern through the pattern history table. So that's the second level, right? Where, right, you use the global pattern as the hint into which table are you going to refer to for the pattern history table. Again, I'll go through the example to make it more clear. This is a paper published in 1993 in the technical report, actually, by McFarlane, right? Called the Combining Branch Predictor. And here's how it works, right? The two-level global predictor, you have the Gshare again, right? The global history register. And it has something to do with the direction I'm taking. We'll expand on that. The rest of this design looks like a branch target buffer that you've seen earlier. The only addition is in this guy, right? The global history register. The second addition is this guy is actually much more complex. How, right? Now the question is how. So let's go through some example. Here's our code, right? For I equals 0, I is less than 5, I is plus plus. If I is less than 3, you take this branch. So this is the first branch, right? The loop is the first branch. This is the second branch, and this is the third branch, right? So let's assume if you go into the loop, that's taking the branch. If you go into the if part, that's taking. So if you do if, that's taken. If you do else, this is not taken. And if you loop, it means you take the branch. So let's assume that's our assumption. If it's a loop and you go into the loop, that's taking the branch. If you have an if else, you go into the if, that's taking the branch. If you go to the else, that's not taking the branch. Then, what's the pattern of this program? What's the first decision that happened in this program? Is it taking or not taking the branch? That's a loop, right? So we take the loop. You take the loop. For the first if else, are we taking that branch or not? We're also taking the branch, right? So this is the part where this is the part where I equal 0, right? This is the loop. This is the first if, and this is the second if, right? Now for I equals 1, when I equals 1, you take the loop, right? You take the if, you take the second if as well. So this is when I equals 1. Now let's do what happened. You iterate the loop again when I equals 2, right? Now you take the loop. You take the first if and you don't take, not false, my bad. You don't take the second if, so it is not taken. This is when I equals 2. Then you take the loop, not take the first if and the second if, so this I equal 3. Then you take the loop, not taken, this I equals 4, right? And then I plus plus I equals 5, you don't take the loop. The last one here is you exit the loop. All right. So that's our pattern of the program. We take, not taken, take, not taken, not taken, taken, not taken, not taken, and you exit the loop, which is not taken. Any questions so far มีคำถามอะไรไหมครับสำหรับ pattern ตัวนี้ เพราะเดี๋ยวเราจะเล่นกับ pattern ตัวนี้แล้วดูว่าไอ้ global history register มันทำงานยังไง มีคำถามอะไรไหมครับ อันนี้มันตัวอย่างเฉยๆนะเผื่อตัวอย่างมันไม่เคลียร์ All right, no for now, right? So we'll leave the second example. That's for you to do as an exercise. If you want to try that, we'll do the example 1, right? And let's assume we have 2-bit. We have 2-bit for the global history register. And we use 2-bit saturation counter, as we have seen earlier, the 2-bit state version, right? The predict strongly taken, strongly not taken, those things. All right. And I'm gonna the next thing is I'll copy this pattern. I'll copy this pattern, right, to the next page. So we take the loop, take the if, right? When I equals 1, take the loop, take the if, take the if. When I equals 2, we take the loop, take the first if, not take the second if. When I equals 3, take the loop, not taken. And when I equals 4, right? Taken, not taken, not taken, and then exit the loop at the end, which is not taken, right? This is when I equals 0, I equals 1, I equals 2, I equals 3, I equals 4, and then this is exit the loop. Now the Gshare can be initially can someone give me a random initial condition? It's 2-bit. Each bit predict it just either taken or not taken. So this is the first bit. The 2-bit Gshare. So let me just erase this. And let's assume initially Gshare use taken. Let's assume it's used taken. And let's assume inside our machine, taken is 1, not taken is represented by the bit 0. Whenever I see the bit 0, it means not taken. Whenever I see the bit 1, it means that it's taking the branch for the prediction. Inside here, right, we have the local counter. So this is a pattern history table. And I'll write the prediction, I guess, in orange text here. This is my prediction. Here's my prediction. And let's assume everything initially is initialized to strongly taken, right? 1, 1. So this is strongly taken. Now, how does Gshare work? You go into the first branch. The way it works is I would first look here in the Gshare. I'll first look here. That's the first step. The first step, I look at Gshare. What's the value in Gshare? Can someone tell me what's the value of Gshare? Is it 0, 0, 1, 1, 0, 1, 1, 0? Again, taken is 1, not taken is 0. So what's the value of my Gshare? 1, 1, right? Because it's taken. And as I said earlier, let's assume taken is bit 1. So it's 1, 1. If you look at the pattern history table, you will see, right? You will see that the second step here is look here, and pick the row that match the Gshare. So you have 4 rows, right? Row A, row B, row C, and row D in the table. Which row match the Gshare? Row A, row B, row C, or row D? Row D, right? Then you just check there and look at that. What's the state is in? Strongly taken, right? So what's my prediction if I'm in a strongly taken state? Taken, right? Because I'm in a strongly taken state, I'll just follow that 2-bit prediction that we see earlier from the review from lecture 4, right, from last week. And because it's strongly taken, my prediction is strongly taken. So now that's a part of a prediction. The next step, right, the third step is I need to update everything, right? So let me use the blue text here again. The third step here is to update everything. So are we predicting correctly? Are we predicting correctly here? Is our prediction correct? It is, right? The prediction is taken. The reality is actually taking as well. So if you are in a strongly taken state, and your prediction is correct, what state do you move to? Are you staying at the strongly taken, or are you moving to the weakly taken state? Can someone tell me that? Stay strongly taken, right? Then, so that's the pattern history table. You then, when you update the table, you just look at this part, right? And say, hey, we are at strongly taken. We just stay there because it was the correct prediction, right? So we stay there and we stay at strongly taken, right? So over here is 1, 1, right? 1, 1, 1, 1, and 1, 1. Now, how about the Gshare? The way we update the Gshare is this. We kick this out. We move it here. And then we add, what's the last outcome? Is it taking the branch or not taking the branch? Are we taking the branch or are we not taking the branch? Taking, right? So we push the taken to the left. Again, we move the first taken, right, from this bit to this bit. So the taken moved here. The second taken from here moved to here. So that's how we update the Gshare. Now, can someone tell me what's my prediction? What's my second prediction? Now we are done with this guy. We are done with this first branch. What do I predict next? Can someone tell me from this initial condition? Now I run into the second branch. What is my prediction? Again, first step, look at the Gshare. Second step, look at the pattern history table that gives you the prediction. Yeah, it's gonna keep predict taken, right? Well, I meant like what's the prediction, right? So you keep predicting taken because the Gshare is taken and taken. You now look at the row D, and that's strongly taken. So I'm gonna keep predicting that, right? So you'll be predicting taken for this guy, this guy, this guy, this guy, this guy, this guy, and this guy, right? So be taken, 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 taken. How about this guy? What am I predicting? When I equals 2, the first time you will predict that you're taking the branch because you just go to Gshare and it's like strongly taken. So I think it's going to be taking the branch. That's our first wrong move, right? So we predict taken. In reality, it's not taking the branch. So what do I do? Now, how do I update this row? I was in a strongly taken. I predict incorrectly. So what do I do? From 1, 1, right? You now move to 1, 0. You update from strongly taken to weakly taken because last time I see this branch. And this pattern I was wrong, so I don't believe in myself. I'll move from strongly taken to weakly taken. Then the way we update the Gshare, again, we move this taken bit here, right? So taken goes in here. The actual outcome is not taken. Oops, sorry. The actual outcome is not taken. So not taken move in here. So at the end of the day, you have taken, not taken in here. All right. So now we are done with this guy, and we're wrong. How about this guy? How about this guy? Again, look at the Gshare. Gshare would give you the correct row and then look at the prediction. So what are we predicting here? Oh, first of all, what row now? What row are we looking at? We're predicting taken again, right? And we are correct. We are correct here. So let me use the orange text for correct and red text for incorrect. And because we are correct, we keep this guy the same, right? How do we update the Gshare? What does the Gshare look like now? Yeah, the PHT will be strongly taken for that entry. The Gshare would be what? I move n to the left, right? And it was taken. So I put T in here, right? When we are predicting now, the next prediction is this guy, right? This guy right here, right? And because the Gshare is not taken, so that's 0 and 1. That's 0 and 1. Our prediction is going to be again taken because it's going to look at this row, right? And then, oh, okay, we are strongly taken, so we will do taken. And again, that's a wrong prediction, right? A quick note here. The reason why we call this a global branch correlation is every time we are about to predict, for example, if we're looking at this entry, we're looking at this entry, right? You will see that the Gshare reflects the outcome of the last two branch. What are the outcome of the last two branch? Not taken, right? That's the last two branch, not taken, which is the same as the Gshare, right? And we can keep doing this. Basically, now we are predicting incorrectly, so we have to update the table with the new value, right? So it's from 1, 1, we do 1, 0. We then update the Gshare, right? From not taken, right? To taken, not taken, T and N. And then we when the next prediction is this guy, not taken, right? P and N for Gshare, that's 1, 0. So you look at row C. Row C right now is taken. So we're still drunk and predict wrongly for that row. So we predict taken, and we're done with this guy. Because we predict incorrectly, again, you update the entry right here. Oops, my bad. Always try to go to the next page. You update this entry, and that entry becomes 1 and 0. Then you update this, right? From taken, not taken to not taken. Then you predict correctly, because if you look at the Gshare, right? If you look at the Gshare, you predict that it's taken because you look at 0, 0. 0 is already is still initialized to strongly taken. So you predict taken, and you're done with this loop. Now you update the Gshare again, right? You update the Gshare again, and becomes not taken, not taken. Then if you look at not taken 0 and 1, not taken, right? You will predict taken. Let me use the red text for a wrong prediction, right? And then you now update this guy into 0 and 1. So the next time we see this pattern not taken, the next time we see not taken, you will start to predict that we are not taking this branch because we see enough of this pattern and it's always not taken. It changed from used to be taken, now it's not taken. So we'll shift, right? And then you update the Gshare from not taken, to taken, not taken. All right, so now you predict. So you're done. You were just done with this. Now you're predicting this guy, right? Again, taken, not taken, that's 1, 0. 1, 0 is still 1 here. Weakly taken, so we predict taken, right? We predict taken. And the outcome is wrong, so I'm going to use the red text, right? And you update this, change to 0 and 1, right? And now you have the pattern not taken, not taken. And the last branch, which is this guy, right? You look at not taken, it's still at T and T, so you predict incorrectly, you predict taken. And then you change this into 1, 0, into the weakly taken state, right? So what's my accuracy? I predict correctly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 15. So my accuracy is about 66%. It's still really bad, right? But as you run the program, it will start to adapt to each pattern. And then eventually that 66% accuracy would keep going up, The reason behind that is right now, we only have how many branches are we predicting? 16, right? We are predicting 16 branch. We don't have enough information to fill in this Gshare and also this pattern history table with the previous branches information. But once you do that, it would start to go up and up and up to like 90, something like 90%, right? So any questions so far about the global history register and how global branch correlation works? มีคำถามไหมครับ Oh, great question. So the question is, do we always have to initialize everything to strongly take it? No, it just initializes some value because after your program run, everything would warm up and you would have the correct pattern for each entry, right? In a real processor, you're looking at Gshare that's about at least 32 bits long. 16 or 32 bits long. So your PHT is going to be a huge table, right? And when you run a real program, all those entries will keep eventually updated to the correct state. So yes, again, great question. You just basically, these things need more warm-up time. This thing needs more warm-up time, basically. So that from the initial condition that's set to some random value, move to the actual, like actual prediction. นั่นแหละครับก็ถ้าแปลเป็นไทยนิดนึงก็คือว่าพวก two level branch predictor พวกเนี้ยมันต้อง warm up นิดนึงเพราะว่ามันต้องแบบนั่งอัปเดตแต่ละแถวอะแล้วแต่ละแถวมันต้องใช้แบบ branch ประมาณ 4-5 อันเพื่ออัปเดตค่าให้มันตรงเพราะฉะนั้นมันก็จะใช้แบบตอนแรกๆมันจะ prediction มันจะห่วยนิดนึงเพราะว่ามันขึ้นอยู่กับว่าเรา random initial condition ซึ่งเราเซตเองเนี่ยมันเป็นค่าอะไรซึ่งเราเซตเป็นอะไรก็ได้คือแบบเปิดเครื่องอาจจะให้ทุกอย่างเป็น00หมดก็ได้คือเป็นเรื่องปกติมากๆแล้วโปรแกรมของเราอะโปรแกรมเอางี้เดี๋ยวขอลองเทียบนิดหนึ่งนะสมมุติผมรันโปรแกรม1 วินาที 1 second so basically 1 second of your program execution 1 second means that you are running about 1 billion at least 1 billion instruction 1,000 ล้าน instruction นะ and let's assume that 1% of your instruction is a branch you already warm up in that 1 second only, you warm up 10 million branches. Right, so this whole table will be updated and have the most updated version of your branch. Right, anyone here heard about serverless computing and all those like new cloud technology? มีใครเคยได้ยินพวก serverless ไหมครับ คือ serverless เนี่ยมันเป็นการรันพวกฟังก์ชันที่เป็นฟังก์ชันเร็วๆมากๆคือเราสามารถเขียนเป็น lambda ฟังก์ชันในโปรแกรมเราไปรันใน cloud แล้ว cloud มันก็จะหยิบฟังก์ชันนั้นมา call เฉยๆคือมันจะไม่ใช่รันทั้งโปรแกรม so the problem with serverless and branch prediction is you don't run application for seconds or minutes anymore. You run it for microseconds or milliseconds of time. Then your branch prediction will start breaking down again. Now, with serverless computing, this is one of the big problems. How do you fix branch prediction? Because you don't have the pattern, you can't initialize your branch predictor. So your accuracy drop, right? So worksheet number 2 is for the other branch. I'm not going to do it for the interest of time. Feel free to try that and let me know if you run into any questions. All right. But the next thing is now we talk about the global branch correlation. The next question we should always ask is, can we do better? We should always ask, like, can we do better? Right. So what else can we do? We can add more information. For example, there's a paper called Gshare Predictor, which add the branch program counter into the Gshare. So instead of something like this, you have the Gshare, right? That used to search this pattern history table that you seen from the earlier example. You XOR with the PC so that you try to hash your PC information into the Gshare. So that's a Gshare predictor. And the only difference is this, you add the XOR. So you XOR the Gshare with the PC. And with modern processor in the 2000, the XOR information like Gshare is 32 bits, PC is 32 bits. When you do the XOR, it's enough to kind of populate the whole table. And this allows you to kind of tie each branch information into your global correlation and global prediction as well. The next thing is about local branch correlation, right? The local branch correlation is like this. Now, instead of looking at the whole program, I want to focus on each branch individually. Now, the branch outcome, I would assume that is based on the correlation of the past outcome of the same branch. So the goal here, right, is to figure out what should be the history pattern of the same branch. So this is one of the most influential paper on branch predictor in 1991. It's called two-level adaptive training branch prediction. And it used this concept. Instead of the global history register, it used the local history register, which has n bit that represent taken and not taken, the same thing, right? The same thing as a global predictor, but now it's for each branch. Now it's for each branch. So that's the first level. And then the second level is use the same saturating counter for each entry, right? If you want to design, the overall design would look something like this. You have now, instead of the one single thing that's called a Gshare, right? You don't have that anymore. Now you have another table. You have the first table that have the local, like each row in here. So each row in here looks like a Gshare. So each individual row here looks like the Gshare. These are for different PC. Basically, for each program counter, they have now its own version of the Gshare. ก็คือแทนของที่ผมจะมี Gshare ตัวเดียวสำหรับตั้งเครื่องฮะ Gshare ตัวเดียวคราวนี้ก็คือผมเอา PC มาก่อนแล้วผมก็ hash PC ตัวเนี้ย ให้มันวิ่งเข้าไปที่ table ชั้นแรกแล้ว table ชั้นแรกในแต่ละแถวอะมันก็คือทำหน้าที่เหมือน Gshare แต่ละตัว แล้ว Gshare แต่ละตัวคราวนี้ไอ level ที่2เนี่ยก็จะเป็น table ของมันเลย so the second level has its own pattern. Each entry in the LHR has its own pattern history register. So here's my example. So let's go with the same program, right? The same program we saw earlier. So the pattern is taken, and not taken, right? So that same pattern. Second example again, you can do it afterward. Let's assume there are 4 entries for the LHR, right? Each branch is for each entry. So it's 1 per branch. And each entry has its own 2-bit saturation counter, right? Now you have 3 branches. Branch 1 is the loop. Branch 2 is the first if. And branch 3 is the second if. The outcome of my loop is taken, and not taken. The first if is, let me go back. First if is I less than 3, right? So we take, so that's I equals 2, still take, and then not taken. Any questions so far about this pattern? มีคำถามไหมครับตรงนี้ก็คือผมแยกแต่ละ branch เลยคราวนี้เพราะว่าผมมีหลาย LHR หลาย entry ไงแล้วแต่ละ entry มันก็จะเก็บ information ของตัวมันเองเฉพาะ branch ตัวนั้นคือ loop ก็ loop เก็บเฉพาะของ loop ตัว if ตัวแรกก็เก็บเฉพาะของ if ตัวแรกตัว if ตัวที่2ก็เก็บเฉพาะของตัวที่2นะครับ and the way it works is now each LHR works on its own. So first, let's assume everything initialized to taken, right? Always taken. 1 1 1 1 1 1 1 1. Let's do the loop first, the LHR1. LHR1 is taken, and not taken. So my prediction, right? So let's do the prediction here. It will be this. Let me do yellow. I mean orange, right? Taken. Oops. I will predict taken, and then taken at the end because I would look at here. That's the first step. Then I search this table is 1 1. So I look at here. This is predict taken. And that loop is always taking the branch. It's always looping around. So it's going to predict taken all the time until I'm done. Right? So my prediction would be taken. And I have one wrong prediction. The second loop, now I have the if, right? The if is taken, not taken. So initially, it would again predict taken, right? Now the first not taken will update this into 1 and 0, right? And you still predict taken. It will update this to 1 and 0. And then the second not taken, it would update this entry into 1 and 0. Predict taken. This would become, my bad. This will become 0 and 0. For the last loop, again, you do taken, right? And then taken. This becomes 0 and 0. This becomes 1, 0. This becomes 1, 0. Now you look at the last prediction, right? You look at entry 0, 0. The first row is strongly taken, so this is taken as well. This will becomes 1, 0, right? Now here's my prediction as well. Everything is taken. As you can see here, because you have more bits to warm up, right? You need more branches to actually fill in the whole table. You now have multiple tables. It requires a little bit more time to warm everything up, right? So that's our prediction, and that's how the local history register work. right? And you can use a combination of each of these techniques. In modern processor, it uses a combination of these techniques to predict your branch outcome, right? Again, the second worksheet is for you guys. You can try to do the other example on your own. Now, the other more advanced techniques that proposed after the two ideas, the local predictor and the global predictor, are what, right? So the one thing is called the tournament predictor. That's a paper at the IEEE Micro 1999 that talks about the Alpha 21-64 microprocessors. This is one of the most basically one of the most important microprocessor designed back in the day, in the 1990s and to the year 2000. It used both of the things we learned, both the local and the global predictor. I mean, why can't you do that? We can have two designs, right? You have the Gshare and you have the LHR. And then, because we call this a tournament predictor, anyone want to take a guess on how did they pick which one to use? Do we use the local predictor or do we use the global predictor? The tournament predictor is basically pick the better one. We gauge what's my accuracy for the local predictor and the global predictor, and we keep using the better ones. It can be as simple as that, right? But again, as you can see, the hardware design can get more complicated, right? It can get more complicated. So the branch predictor design now will start to consume more and more transistor. Anyone use Samsung phone? Anyone here use a phone from Samsung? So, I'm pretty sure they have a variation of this technique called the Perceptron branch predictor. What's a Perceptron? You guys, many of you here do either AI or machine learning. So what's Perceptron? It is a form of ANN, right? It's a form of way to learn, right? Because I mean, the way you look at branch predictor is a way to predict some outcome, so we can apply machine learning, right, to this idea. So the Perceptron branch predictor is proposed in HPC 2001 by Jimenez and Lin, right? And it learned the direction and the correlation between each branches, but now you use Perceptron and you modify the weight inside the graph, right? And then you basically build the correlation between each loop and each if else, and then you modify the weight. Basically, it's a way to integrate the supervised learning into the branch predictor. It's now actually got the test of time award. I think it's 2017, 18. I think it's got a 2007, 18 HPCA. This paper got the test of time award. When I was at the event as well, I was attending that particular HPCA, and the guy who invented this, which now becomes a professor, came in and actually told us that, yeah, it's actually one of the branch predictor used by some of the phones company that you've been using, right? So this is basically how you can actually envision, right, your paper that you've done actually now evolve into an actual product after 10 or 15 years, right? And to be honest, the process can be long, right? You try to invent new idea, and to actually realize the idea can take multiple years of that. All right, so we would then talk about other way to handle branches. But before we go there, let's take a maybe 10 minutes break, because we just do a too long example with a few more types of branch predictor. Before we go into, okay, what can we do? Can we not predict, right? Can we do something that doesn't have to do with prediction? We'll pause the recording here.